Hey everyone. First of all, thank you for being here today. My name is Samji Samira and I'm a fifth year graduate student working with Professor Aranda Nicola at the Department of Chemical Engineering and Material Science at Wayne State University in Detroit. It is my pleasure today to discuss about some of our recent efforts on developing design strategies for oxygen electrocatalysis on non-stoichiometric mixed metal oxides. The emphasis of today's talk is going to be on identification of measurable oxide properties that can be correlated to their electrocatalytic performance. Let me start off by discussing about oxygen electrocatalysis and why it remains key for a hydrogen-based economy. The hydrogen-based economy primarily revolves around a carbon-neutral way of producing hydrogen and then consuming this hydrogen as the fuel. One of the cleanest and sustainable ways of producing hydrogen is via electrochemical splitting of water that results in oxygen as a byproduct. Shown here is a typical current potential curve associated with water splitting. It is observed that the deviation from the theoretical potential for oxygen evolution reaction is significantly larger than that of hydrogen evolution reaction, thus making OER the overall efficiency determining step in a water electrolyzer. What can then be done with the generated hydrogen and oxygen is the fact that they can be recombined in a fuel cell, leading to the formation of water. Even during consumption of hydrogen as the fuel, it is observed that oxygen reduction reaction deviates significantly from the theoretical potential as compared to hydrogen oxidation, thus making ORR the overall efficiency determining step in a fuel cell. What is also interesting is even at these significant deviations from the thermodynamic potential, the best performing catalysts remain noble group metal based catalysts such as platinum and palladium, thus making their commercial realization challenging. In order for widespread implementation of these technologies, there's a need to move beyond these precious metal based catalysts to something that is cost effective. One particular class of materials that fits this bill is that of non-stoichiometric mixed metal oxides of the general form An plus 1, Bn, O3n plus 1. These oxides are characterized by oxygen non-stoichiometry in the structure. The A and the B sites are generally metals. N can take values anywhere between n equal to 1 all the way through n equal to infinity. When n equal to 1, a typical layered structure called the Radulson-Popper phase is formed, where a perovskite layer is separated by a rock salt layer and the perovskite and the rock salt layer continue on in the z direction. As one moves towards n equal to infinity, a typical perovskite type structure is formed that I am sure most of you have heard about. These oxides are mixed ionic and electronic conducting in nature, thus making them suitable for electrocatalytic applications. Although I told you earlier that the A and the B sites are metals, I did not tell you what phase space they can encompass when across the periodic table. If one were to use the periodic table as a toolbox to identify the A and the B site metals, it is observed that these oxides can encompass 90% of the metals in the periodic table, giving rise to a vast phase space of the order of 10 to the power 19 potential compositions. The A site is generally either the alkaline earth metals or the rare earth metals, while the B site is the catalytically active transition metal. In addition, these oxides can exhibit multiple crystal symmetries, stemming all the way from highly symmetric cubic structure to tetragonal to rhombohedral and the less symmetric orthorhombic structure. This enormous phase space uh, in terms of the compositional space and the crystal structure can affect its electrocatalytic activity. Therefore, in order to identify optimal electrocatalysts for targeted electrochemical reactions, there's a need to develop predictive tools that can determine an optimal electrocatalyst for a targeted electrochemical reaction. Despite these challenges associated with identification of predictive tools, there has been some work towards identification of activity descriptors that serve as predictive tools. For instance, the theoretically calculated adsorption energy difference between oxygenated intermediates O and OH has been shown to exhibit a volcano type relationship with a theoretical overpotential for oxygen evolution reaction. Oxides on the left leg of this volcano are limited by strong adsorption, while oxides on the right leg are limited by weak adsorption. Oxides close to the top provide an optimal compromise between strong adsorption and weak adsorption, thus leading to enhanced catalytic performance for OER. One of the challenges associated with such theoretically calculated descriptors is the fact that it is challenging to estimate the adsorption energies of reaction intermediates experimentally. In order to overcome some of these limitations, there has been some work towards identifying experimentally measurable descriptors. For instance, the Eg orbital filling of the transition metal in the oxide has been shown to exhibit a volcano type relationship with the experimentally measured electrocatalytic activity for oxygen reduction reaction. It has been shown that an Eg orbital filling close to 1 provides an optimal compromise between strong adsorption and weak adsorption, leading to enhanced catalytic performance. One of the challenges with such descriptor is the fact that the Eg orbital filling is determined from the bulk oxidation state of the transition metal cation in the oxide. Since catalysis is a surface phenomena, there is a need to move towards identifying surface factors that determine the electrocatalytic activity. In addition, what is also interesting is oxides with different B sites like Mn, nickel, and cobalt have been shown to have very similar Eg filling, which also means they would have similar electrocatalytic activity, which may not be true as I will show in the later part of my slides. One common theme between the two descriptors is the fact that both mainly study the electrocatalytic activity while providing limited insights into the stability of the oxides. With that, we set off by asking the following question. Is it possible to identify experimentally measurable oxide properties of working oxides that can describe both their electrochemical activity and stability while using oxygen reduction reaction as a probe reaction? We propose to combine theoretical and experimental tools to bridge the gap between the two. Our approach involves a correlated interplay between synthesis and characterization using some of the tools that are listed here, in combination with detailed electrochemical measurements and surface property measurements. These two are then used as a feedback loop into theoretical calculations using atomistic modeling and some descriptor type analysis. We start off by studying n equal to infinity type perovskite oxides because these have been widely studied for electrocatalysis. We choose lanthanum as the A site because of its high electronic conductivity amongst the rare earth metal oxides, and the B site is varied all the way from chromium to nickel amongst the 3D metals due to their cost effectiveness. In addition, varying the B site metals from chromium to nickel gives us an opportunity to study the effect of crystal structure as it varies all the way from rhombohedral to orthorhombic symmetry. In order to synthesize these oxides, a sol-gel based method is used, where stoichiometric amounts of the A site salt, which is basically lanthanum in this case, and the B site salts are dissolved in water. Citric acid is then added as the chelating agent to bring the metal ions together. And the resulting solution is heated at 85 degrees Celsius, resulting in the evaporation of water and the formation of a gel. The formed gel is then burned and calcined at temperatures of interest to form oxides of interest. A typical sol-gel type synthesis results in the formation of polyhedral shaped particles with an average particle size of 50 to 100 nanometers. We then combine these studies with some selected area electron diffraction measurements from a transmission electron microscope to identify the surface structure of these oxides. It is observed that on a rhombohedral surface, a 1,0 - 2 transition metal oxide terminated surface is dominant, while on that of on an orthorhombic structure, a 0,0 - 1 transition metal oxide surface is found to be dominant. Initially, we start off by studying the effect of crystal structure on the electrocatalytic activity. One of the good things about LaMnO3 is the fact that it can be synthesized in two different crystal symmetries based on the calcination conditions. We then move on to study the electrocatalytic activity towards ORR and find that there is an 80 millivolt difference in the onset potential between the orthorhombic and the rhombohedral crystal structure, suggesting that the crystal structure plays a crucial role in determining the electrocatalytic activity. We then benchmark our experimental observations with theoretical calculations. A 1,0 minus 2 manganese oxide terminated surface is used to model ORR on rhombohedral LaMNO3, while a 0,0,1 manganese oxide terminated surface is used to model the orthorhombic structure. A 4-electron ORR mechanism is modeled where O2 is initially protonated to form a surface adsorbed OOH. The OO bond in OOH is then cleaved to form a surface adsorbed O. The surface adsorbed O is then protonated, leading to the formation of a surface adsorbed OH. The last step involves the desorption of this adsorbed OH, leading to the generation of a clean site. It has been well established that for catalytic systems that are limited by weak adsorption of oxygenated intermediates, O2 protonation to OOH is the rate limiting step. While catalysts that have strong binding of oxygenated intermediates are limited by OH removal to generate a clean site. We then convert these atomistic simulations into a free energy diagram. It is observed that on both rhombohedral and orthorhombic LaMNO3, OH removal to generate a clean surface site is the potential determining step. The difference in adsorption energetics between the two leads to a 70 millivolts difference in the theoretical overpotential, thus benchmarking our experimental observations. The difference in this adsorption energetics and the theoretical overpotential is attributed to the nature of distortion in the two different crystal symmetries. We then study the effect of the B-side composition in these oxides while varying the B-side from chromium to nickel. A significant difference in the ORR onset potential is observed, suggesting that the electronic structure of the B-side cation in these oxides plays a crucial role in determining the electrocatalytic activity. Similar to earlier, we benchmark our theoretical calculations using a free energy diagram. What is observed is oxides to the left of Mn, including Mn, are limited by strong adsorption of oxygenated intermediates, leading to OH removal, generating a clean site being the potential determining step. While oxides to the right of Mn, including cobalt and nickel, are limited by weak adsorption of oxygenated intermediates, thus making O2 protonation to OOH the potential determining on these oxides. One can then convert such free energy diagram type analysis into a volcano type analysis, where the binding energy of oxygenated intermediate O exhibits a volcano type relationship with the theoretical overpotential. Oxides on the left leg of this volcano are limited by strong binding, while oxides on the right leg are limited by weak binding. This is consistent with previous literature reports. What is also interesting is the binding energy of oxygen scales linearly with the oxygen vacancy formation energy, which describes the oxide surface reducibility. This suggests that one can then use the surface oxygen vacancy formation energy to describe the electrocatalytic performance. The negative nature of the slope in this case inverts the weak binding and the strong binding legs. Oxides on the left leg are now limited by weak binding, while oxides on the right leg are limited by strong binding of oxygenated intermediates. One of the good things about surface oxygen vacancy formation energy or the oxide surface reducibility is the fact that it is possible to estimate it experimentally. One way to estimate the oxide surface reducibility is via hydrogen temperature programmed reduction. In a typical H2TPR experiment, a certain mass of catalyst is loaded in a reactor under the flow of a reductant such as hydrogen balanced with helium. The oxide is then heated all the way from room temperature to 900 degrees Celsius in our case, and the hydrogen consumption as a function of temperature is monitored. Two distinct hydrogen consumption peaks are observed, one at relatively lower temperatures of 730 Kelvin, the second one at relatively higher temperatures of 1063 Kelvin. If one were to stop the TPR after the second peak and XRD the oxide, it is observed that, for instance, LaMNO3 is completely reduced to a mixture of La2O3 and MNO. While if one were to stop the reaction after the first peak, the bulk crystal symmetry is found to be intact using X-ray diffraction. Combining these bulk studies with some surface characterization tools such as X-ray photoelectron spectroscopy, what is observed is pristine LaMnO3 has a combination of both Mn3 plus and 4 plus in the near surface region, while post surface reduction after the first peak, the Mn4 plus represented in the pink curve here is shown to be absent, thus suggesting that the surface is reduced. Therefore, the temperature at which the first peak occurs is associated with the oxide surface reducibility. We then go on to study the effect of the B site composition while varying the B site all the way from nickel in LaNiO3 to chromium in lanthanum chromium O3. What is observed is as one moves from nickel to the left of nickel amongst the 3D metals, it becomes challenging to reduce the oxide, as indicated by an increase in the oxide surface reduction temperature. What is also interesting is the surface reduction temperature scales linearly with the theoretically calculated oxygen vacancy formation energy as well as the theoretically calculated binding energy of oxygen. Therefore, all this suggests that one can then use an inherent oxide property such as the metal oxygen bond strength as described by the surface oxygen vacancy formation energy or the surface reduction temperature to describe the electrocatalytic activity. One can then use the empirically measured oxide surface reducibility in terms of surface reduction temperature to describe the empirically measured electrocatalytic activity of these oxides. A volcano type relationship is observed between the surface reduction temperature and the ORR onset potential. Oxides on the left leg of this volcano are limited by weak adsorption of reaction intermediates, while oxides on the right leg are limited by strong adsorption of oxygenated intermediates. What is also interesting is for n equal to infinity type perovskite oxides, the oxide surface reducibility in terms of surface reduction temperature captures effects from the A site composition of these oxides as well as the B site composition, thus making them universal in describing the activity of n equal to infinity type perovskite oxides. What is also interesting is the surface reduction temperature captures effects from n equal to 1 type Radulson-Popper oxides of the form A2BO4, having a pure A site or a mixed A site and a series of B site metals. Since n equal to 1 and n equal to infinity type perovskites can be described using oxide surface reducibility in terms of surface reduction temperature, this suggests that oxides in between with n equal to 2 all the way through n equal to infinity can also be described using such a descriptor. Lastly, this descriptor captures effects from the crystal structures stemming all the way from rhombohedral to orthorhombic to tetragonal structure, making oxide surface reducibility global in describing the electrocatalytic activity across a family of oxides. I initially set off with asking the following question where I wanted to describe both the activity and stability of these oxides. Although I mainly describe activity thus far, I'll shed light into describing the stability of these oxides. What one can think of is oxides on the left leg of this volcano, characterized by low surface reduction temperatures, exhibit weak metal oxygen bond strength, thus can be easily reduced, while oxides on the right leg exhibit high surface reduction temperature, which suggests challenges with reducing such oxides. In order to validate the hypothesis, we studied the stability of oxide on the left leg, for instance, La cobalt O3, using a DOE suggested accelerated stress test. It is observed that lanthanum cobalt O3 exhibits a significant loss in electrochemical performance over 30,000 cycles of cycling. It's close to the top, like rhombohedral LaMnO3, provides an optimal compromise between activity and stability. LaMnO3 meets the DOE criteria of less than 40% loss in activity over 30,000 cycles, thus making it active and stable. This suggests that the oxide surface reducibility can be used to describe activity and stability across a family of mixed metal oxides. To conclude, I'd like to remind you that I initially started off with defining the problem statement as identification of measurable oxide properties to describe the electrocatalytic performance of these mixed metal oxides using electrochemical oxygen reduction reaction as a probe reaction. It is observed that both the crystal structure and the composition of the oxide affect the electrocatalytic activity. These experimental observations were then benchmarked uh, using fundamental insights from atomistic simulations. These theoretical calculations suggested that the oxide surface reducibility, which is an inherent oxide property, uh, can be used to describe the electrocatalytic activity of these oxides. The oxide surface reducibility was then estimated using H2 temperature programmed reduction, where the first peak was associated with the surface reduction. A linear scaling relationship between the experimentally measured surface reduction temperature and the theoretically calculated vacancy formation energy and the binding energy of oxygen was observed. All this was brought together in identifying surface reduction temperature, which is an empirically measured property, to describe an empirically measured electrocatalytic activity of these mixed metal oxides using oxygen reduction reaction as a probe reaction. The value of this work is twofold. What I mean by that is such activity descriptors can be extended to other catalytic reactions, such as high temperature CO2 electrolysis using these mixed metal oxides, as well as high temperature oxygen reduction and evolution reactions in solid oxide fuel cells and solid oxide electrolyzer cells. The volcano would hold good. The only thing that would change is the optimal composition close to the top would shift based on the temperature of interest. I'd like to conclude by thanking the US Department of Energy for providing the financial support with this research. I'd also like to thank the AICHE CRE division for providing me with the travel grant to attend this annual meeting. I'd like to thank members of the Nicola Lab for their support during this research, as well as Wayne State University for providing some of the tools. I'd like to thank my advisor, Aranda Nicola, for being instrumental and supportive in the publication of this work. I'd also like to thank my friend Shankwi, who did most of the theoretical calculations that I showcased here. If you have any questions, you can reach out to us. This is our website where all our email addresses are listed. In addition, you can tweet out to us, to me directly, and my Twitter handle is Samji Samira. You can tweet out to our lab. The Twitter handle for that is Nicola Lab, or you can tweet my advisor directly at Randa Nicola. With that, I'd like to thank you for your attention, and I hope that you learned something new today. Thank you very much, and have a great day ahead.